Okay, let's do a nice clean take. Okay, so like I don't have to crop anything out, which means that I'm gonna be very PC this time around during the tutorial. So hopefully, like, you know, everything that I say that's recorded is like things that I'm okay with. So yeah. Good morning, everyone. Welcome to another tutorial. Okay, so here's the plan for today. In case you didn't see in chat, what I'm gonna quickly do is run through like solution sketches. So they won't be like horribly in detail, but they should be like the solution sketches for your assignment. So like again, they won't be in detail, but they'll basically be the main idea. If you can get these things working, then if you can like roughly get the main idea, I trust that you guys should be able to implement it. So I'll roughly be telling you what the recurrence should look like, and how you should be storing in a table, like how you should be indexing into a table to store the solutions. All right, I'll do this like for like some of them, not all of them. I don't think all of them are horribly interesting. And then we'll talk a bit about greedy problem solving in general. All right, just in case you've like either not seen the lectures, or you know, like me giving you extra problems with like my take on it, so that at least like you get some idea of like what I talk about during tutorials usually for this problem. Is that all right? Any hard objections before I begin? Soft objections work fine too. Let's see. Yep, seems good. Okay, cool. Thanks for the reply. Good morning to you. Okay, let's see. Let's begin. Right. One thing that I actually did want to mention that I actually almost forgot to mention was that you might be wondering like why DP. Right. Thus far, the kind of motivation that I've been giving you is that like you know, like, oh, okay, so we know we can speed up problems, but which one of us is really going to be like solving for coin change anyway? You know, like unless we're writing an app on coin change, you know, why do we need DP? You know, all the rest of the problems seem kind of weird, right? They seem kind of abstract, which is something I kind of agree with. Like they're actually really abstract, and you probably wouldn't see them in real life. And again, because I'm a mathematical person, I don't really tend to care too much. But you know, you as a student, like you, dear student, might actually care, because you know, you guys will be working on real world problems, and I'll be sitting in my basement like staring at math. So let me give you one really concrete reason. But again, because like I don't really work on practical stuff, I'm not really sure how applicable this is. But this is like as close as as a concept as I can mention to the light of day, right? So like I'm doing my best here. Please don't please give me some credit for that. So DP, besides like for example coin change, which you might think is horribly uninteresting, is also used for something called the CYK algorithm. So this is I think it's like called Younger Kasami, something like that. You can look it up. This thing is what you use to parse, is used to parse what we call context-free grammars. All right. So if you don't know what this is, right? Because you might be thinking, oh, this is just like yet another like one of those like mathy things. Well, you're not wrong. It is kind of mathy, but it's like more like, okay, it's more linguistics than math, but it kind of looks like math. But this is something that happens that should happen in your daily life as a CS student, like almost like every day. When you're running your compilers, for example, okay, when you're running your compilers, they're not exactly parsing a context-free grammar. Like sometimes, you know, people argue it's technically context sensitive. Like C++, I think, is context sensitive. Oh no, C++ is like Turing complete, I think. Okay, I really can't remember. But conceptually speaking, your compilers are running some version of this. Right, and I think like this algorithm is a pretty cool one. And if you ever have time, or if you're ever interested in like programming languages, that sort of thing, and you want to learn about like parsing them, for example, or like the kind of algorithms that we use, this is one of those. This is really one algorithm that they use. And what was I going to say about this? If you, no, I already said that. If you want to learn about this, yeah, you can look it up. Yeah. So yeah, I mean, I think, I'm not sure if compilers or like parsers still implement this, right? But I do think that this is a very well-known algorithm in that aspect, right? So yeah, there you go. DP, like that uses DP. Like if you're curious, you can look it up, right? Learn about the formal problem definition, which I'm not gonna state here, and then you can like sort of like figure out why we call it DPA. You know, that sort of thing. But like, you know, I trust that like once you know what the problem statement is and the kind of input that you're given, you should roughly be able to figure it out. All right. Okay. So let's begin. Problems. I have 3 problems that I'm supposed to cover. Right. One is the block one. One is the like the solid block one. One is the, what was the other one? I'm trying to remember. There was the bracketing one. Okay, I don't know why my handwriting is so bad today. And the what's the last one? The group. Like, you know, I can't call it a group. Just call it multiplication. I actually thought it was a group, so that actually gave me one extra assumption to use, and that extra assumption actually slowed my algorithm down. As in, like it like with that assumption it'd be fast, but without that assumption, like my algorithm would be a bit slower. So I actually had to fix it a bit. Am I missing out? Am I missing out any problems? Like I'm gonna skip the subset sum one because that one should roughly be straightforward, right? And the coin change one should be like straightforward. It's like a giveaway question, right? Am I missing anything? I don't think so, right? So it should just be like finding the largest like square, solid square. Like I'll talk a little bit about bracketing, not too much, and then like something about multiplication. Okay, no one's saying anything, so I'm assuming that means that I'm not missing it out. I'm not missing out. Cool. All right, so let's do the block one first. Now like I'm gonna mention, it's 9:10 right now, right? My friend, my colleague TA told me that like it will be impossible for me to finish 3 questions within 20 minutes and then talk about greedy later on. So let's see how far I can get. All right. So let's say I give you a grid, and this grid is, Jesus, every time I swear, every time. I need to reposition my tablet so that it's like somewhere where it doesn't do that funny shifting thing. Okay. So let's say I've been given a rectangle, right? And I want to find out what's the largest possible square I can make with the corner here, like with the bottom right corner here. Okay. And the way that you're gonna, like, if you think about it, the idea behind this is that when I'm looking at, or like when you're looking at, or when your algorithm is looking at this spot, right, it should be of 2 possible colors, right? So this can be of like either color 1, a color 0, or color 1, let's say. Okay, now right off the bat, if you look at these positions, okay, and either of them have a different color than you, right? So if, let's say, for example, without loss of generality, this was color 0, and like either this one, or this one are color 1, right? Then you know that you can't make a square. You can't make a square larger than like 1 by 1 at this right hand side, like this right corner, right? So you can forget about making a square. So the size of the square here should be 1, right? Like the dimension should be 1. So in the corresponding part of the DP table, you should just put 1. Does that make sense? Okay. I mean, okay, like think of this as the DP table and think of this as the actual table. and like they're supposed to be the same size, but I made a mistake. Okay, so the interesting case is when they're all 0, right? When it's all 0, the only question becomes like, okay, how far can you make this, right? I argue you have 3 cases. Okay, and the way that I'm gonna draw it is, use a different color. You have this to be worried about, you have this to be worried about, and you have this to be worried about. Okay, so the largest possible square that you can make, okay, wait, let me mention. So you have 3 possible values to be looking at now, A, B, and C. Okay, this value A here, right, corresponds to the largest possible square you can make with the bottom right corner being here. Okay, being here. B corresponds to the largest possible square that you can make with the bottom right corner being here. And C corresponds to the largest possible square you can make with the bottom right corner being here. Okay, so you see, like, what you know is that if you have the same color, right, everything here is going to be like all zeros. And everything here is going to be like all zeros. Everything here is going to be like all zeros, right? Okay, A tells you how far up the zeros go. Okay, C tells you how far left the zeros go. and B tells you how far like in up along this diagonal the zeros go. Okay, now the square that you can make here is bottlenecked by all these three, right? If let's say like one of these was any shorter, then you can only make a square that's like as large as that, right? So in other words, if you have the same color, right? If you look at these three and you realize that you have the same color, right? Your value here should not be 1, right? Instead, it should just be the minimum of A, B, and C plus 1. Does that make sense? Right? Because I mean, like I know this guy gives you a square, but you don't really care about the square, right? You only care about like this how long this line can be, like of the same color. As it turns out, when you find the largest possible square, it also gives you the largest possible. I mean, it doesn't give you the largest possible line, but it gives you like a bottleneck, right? And you know that you can't make a what's the word? You can't make a square that's larger than that, because if let's say like at this point you might be wondering, okay, let's say this was color 0, this is all color 0, right? And let's say that like this was also color 0, but my square tells me I have this length, not +1. Isn't that an issue? The answer is no, because the reason why this was a square in the first place was because probably somewhere along the way this must have been a 1. Like there must have been a 1 in one of these locations, right? And because there was a 1 in that location, you can't extend this square further up, which means that this guy can't extend like his version of his like his length of his square further up as well. Does that make sense? Okay, so this is the rough idea, right? So take the min of this guy, this guy, and this guy, then add 1 to it. Wait, do you add 1? I think you do add 1. You might not add 1. Work out the details yourself. All right. So this is the solid square question. That's the idea. All right. If you see in this manner, you realize that the DP table is just okay. I need the bottom right corner for this guy. I need the bottom right corner for this guy. The bottom right corner for this guy. The bottom right corner for this guy. So these are the values on the DP table you look at. Right. This is the table. This is the table. This is the DP table. Okay. Okay. Next question. Bracketing. Okay, so for the bracketing one, okay, let me see how fast I can do this. So for the bracketing one, right, you're given like, for example, just pretend that you're given like some symbols A1 to AN. We don't really care what the symbols are. They can be X, they can be whatever, right? For the binary bracketing case, you can think of this as trying to overlay a binary search tree over it. I mean, sorry, not binary search tree, a binary tree over it. And every time you do a binary bracketing, right? It's really just you like defining a node here and dividing the like like these things into a binary subtree and these things into another binary subtree. Right? My tree is upside down right now, but you get the idea, right? So how many ways are there to do this? Like we right now, if we just want to count, right? If this is just a combinatorial question, right? You have to draw the brackets on the outside. Then what you do is that you can sort of like drag this slider along and say, oh, I could have made the bracketing this way, right? But hey, that's not the only way. I could have made the bracketing this way, so on and so forth, right? And remember each time that you do this, you're sort of like saying, okay, like now that I've done this binary bracketing, I need to like binarily bracket everything else. Does it make sense? Right? So this is a very natural, I'm solving for my subproblem kind of deal. Okay. So what this means is that we are like, how many subproblems do we have? We have like this kind of subproblem, and then like if we slide the slider along, we have like this subproblem. If we slide the slider along again, we have like this subproblem. If we slide the slider along again, we have like this subproblem, so on and so forth, right? And then like the last problem that you have to deal with looks like this, right? Where this is AN, and this is A1 to like AN minus 1. Right? And so if I want to solve for Fn, right, this is going to be F1, this is going to be Fn minus 1, this is going to be F2, this is going to be Fn minus 2, n minus 2, that's right, so on and so forth, right? So what this means is that your solution should really just look like recursively, your solution should just be like Fn looks like this funny summation, Fi, Fn minus I is equals to 1 to n minus 1, something like that. Right, now this clearly has overlaps, right? So what do you, but realize that we're only gonna ask for n possible values, so you can just have a table size, like of length n, right? And then you can initialize it with like some dummy value, let's say like -1 or something, right? Then just run the algorithm. If the algorithm sees -1, it means that we've never filled that value up before, so you can make a recursive call on it, quote unquote recursive call on it. Or what you can do is you can do bottom up, so you can fill up the values as needed, and then what will happen is that like you know, you can start the previous value and just use this recursive definition to figure it out, right? So the number of states you have here is n, and the number of time it takes to compute the next cell is going to be n as well, because you need to iterate backwards, right? So this should just take O(n) squared time. Okay. Oh no, it's already 9:20. I'm running out of time. Okay, so let me quickly mention for the general case, right? For the general case, the solutions might not make sense. Like they might look very weird, but really that's the explanation I will give as well, right? Which is that like you treat it as like two possible cases. Either you're gonna bracket it binarily or you're not. And in the case that you're not, you can sort of pretend, quote unquote, that you're bracketing it binarily. Like you're still sort of like drawing this divider as to like, okay, this is going to be like the last portion that's bracketed, and then the rest you're free to do whatever you want to it, right? Being free to do whatever you want to it, right, is in and of itself some form of like general bracketing, right? This like just walk into the solutions with this in mind, and the rest should make sense. Okay, now let me quickly finish. Let me see if anyone has any questions. No one has any questions. Okay, let me quickly do the last one. So for the last one, what you want to do is you want to have a DP table, right? That says IJ, IJT, something like that. This says that using elements from AI to AJ consecutively, of course, right? There exists a way to bracket it. Like there exists a way to form like parentheses such that when you do that and you did the multiplication, this is equal to T. Okay, so I think like the way that I did it actually required like some assumption on it. I thought it was a group. Turns out it wasn't a group. For those of you who don't do math, like you know, just pretend that I'm saying like a bunch of stuff that doesn't make sense. But yeah, I mean, like I needed the assumption that you need a group for my algorithm. The actual algorithm doesn't need it, so you have to tweak the solution a bit. So the way that it works is that you're given some string, and let's say you're just given like the multiplication table. Let's just call it G, right? And last time what I did was I had FSGT, something like that, right? Okay, this time like I think it actually makes more sense if you return just the list of elements that you can construct out of it, right? Then the intuition should just be that given like let's say you're already at like AI to AJ, right? Again, you can think of the splitting idea. How it works is that there's going to be some place for you to like draw parentheses, right? So that you can multiply these two items. Okay, and then what you can do is that you can solve the left half and the right half recursively. This should give you a list of items that you can make, and this should give you another list of items that you can make. Okay, now giving you these two lists of items that you can make, this is of size at most k, this is of size at most k. Now from these two, you can construct a combined list of items that you can make using AI to AJ. And you can do this in OK squared time, right? Because this is just take every item in L1 and multiply with every item in L2 and just union them into this list, right? So how do you store this list, right? So the list is just going to be stored at IJ, DPI, DPJ, T, right? So to get the list, right, just iterate over all the possible T's. Every time it says 0, you know you don't make that item. Every time it says 1, you know you make that item, right? That's how you construct it. So once that's how you obtain it, right? So like once you've obtained these values, then what you do is that you just basically multiply and then do the same thing, right? So for every item that you see here, you're just going to set the corresponding bits to 1 or 0. This is pretty much like the quick and dirty idea, right? So going in, if you realize how this works, that's just how you're going to solve the problem. Nothing terribly intelligent there, right? So why is it n, what's it, n cubed k squared, or was it, yeah, n cubed k squared? So the reason why it's n cubed k squared is because the DP table size is like n squared k or something, right? But you shouldn't be counting this k when you're like sort of like constructing the solution, because the reason it's kind of annoying to explain why, but it's kind of like you actually don't like this part of this k, right? Like in the state is kind of also part of like the k squared in your computation. in the sense that like you should really think of it as for every pair ij, right? I'm going to construct like for every ij, we're going to construct a list of items to make, like items you can make, right? Constructing this list takes nk squared time, right? And there are like, you know, like theta n squared possible pairings of ij. So this is just n squared times n times k squared, which is like n cubed k squared. All right. Okay, if that was too fast, like you can look up the video. I want to move on to greedy. All right. If you have any questions, please don't send them here. Like for this week, send them to Telegram, right? And in case you're gonna forget, send them now. Okay. Then I'm 5 minutes overdue. Wait, am I 5 minutes overdue? No, I'm 5 minutes too early. I targeted 9:30. Okay, I guess I have time for questions. Does anyone have like any rough questions? Does everyone get the idea? Like, I really just want to present the proof idea, not the not the full thing. Like, I've told you roughly like what you're supposed to look for, what the recurrence should kind of look like, and how you should be indexing to your table. That should be like all that you need to construct the solution. Does that make sense? Cool. Okay, let's move on. Extra 5 minutes is always good. Let's talk about greedy. Okay, so I wanna clear up a misunderstanding because I'm not sure if Divesh talked about this, right? So stop me if you really like if all of you understand this and I don't have to go through it again. But did any of you notice that the proof for like greedy choice versus optimal substructure looks very similar? Or like did that thought ever occur to you? Like when you're proving greedy choice, it's like, hey, that kind of looks like optimal substructure, you know, like, but
the lectures did teach us optimal substructure.
Wait, so then, but I thought some people said that you did. Okay, I mean, well, okay, at the very least, since you did know optimal substructure going in, did you feel like it was similar? Just out of
Yeah, I only
curiosity.
knew there was optimal substructure because it was mentioned in your chat.
Okay. Wait, but I mentioned it in class as well. Okay, anyway, um, let me clear up a misconception right off the bat. For those of you who remember what I talked about with optimal substructure, all right. Optimal substructure, remember, it says that you want to solve your subproblems optimally because so you should be solving subproblems optimally, right? To solve you know, your own problem optimally. Right? So another way of saying it, which is the way that CLRS put it, is that if I have like the optimal solutions to my subproblems, okay, I should be able to reconstruct, or I should be able to use that to construct an optimal solution. All right. Now, greedy, on the other hand, right? Like, and if you remember the proof, it went along something along the lines of, okay, assume that I didn't solve my subproblems optimally. Now let's swap it out for an optimal solution and show that it all works out, right? That we get an even better solution. And the idea is that when you do this swapping, you don't really hurt yourself in any way because the subproblems are like quote unquote kind of independent, right? And if you don't remember this, like I actually linked screenshots to the relevant pages on CLRS in the group. So have a look at that. I highly suggest you really do take a look at that. Now the greedy choice, on the other hand, right? Like if you've watched the lectures, right, should kind of follow a very similar spirit in proof idea, which is kind of like, okay, I should be making this greedy choice. Why should I be making this greedy choice? Assume not. And then you know, you'll do this whole swapping idea again. Oh, you know, like, okay, let me swap out like whatever choice I made for my greedy choice, and then I'll show that I get an even better solution. Right. So perhaps like for some of you guys, you might be thinking, what gives this is the same thing, right? Is optimal substructure basically greedy choice? The answer is not really. Let me draw it pictorially. So let's say I have some problem P. All right, so let's call it problem P. And problem P, let's say, kind of relies on different versions of the subproblem. So maybe like subproblem 1, subproblem 2, subproblem 3, what have you, and so on and so forth, right? Okay, let's limit it at 3 for now. Okay, so remember that subproblems are kind of like my subproblems are me trying to solve the same version of my current problem but smaller, right? So there's really, of course, many possible ways that you can phrase it. In the knapsack way, we said a subproblem is kind of like my problem, but with one item removed, right? With item one removed, for example. That's what I'm trying to get at. Okay. So subproblems are really for up to you to define like what are considered subproblems and how you should be solving them. Okay. Now, optimal substructure just says that, hey, if I decompose my problem into subproblems in some reasonable manner, in knapsack we said it's either with item one in the knapsack or with item one not in the like without item one in the knapsack, right? So that's up to you to define, right? If you could define your subproblems in such a reasonable manner, right, and you solve them optimally, it should help you should be able to reconstruct a solution from it. Okay. Greedy choice, on the other hand, says something different. Greedy choice doesn't actually talk about solving your subproblems optimally. What greedy choice is that if I have my subproblems, right, okay, I should not actually have to go through all of them. Let's say that I had some very natural and reasonable way of decomposing my subproblem like this. Okay, then what's going to happen is that one of them should be the only one that I need to look at, and the rest are irrelevant. In other words, you have this choice about which subproblem you should be referring to. And even though from a DP perspective or from a recursive perspective, the others might make sense. Like you might think, okay, I should be considering this case, I should be considering this case, I should be considering this case, right? As it turns out, the structure of the problem is so that you actually don't need it. Okay, so right off the bat, let me quickly mention some of the problems that you should have or could have seen already that do use like this greedy idea. MST solving. This is like right off the get-go. For coin change, I think it's in your assignment as well. Okay. Now let me just say one thing about it so that like at least when you walk into the assignment, you're not confused, right? You might be thinking, okay, in the previous assignment, you told me that greedy doesn't work. So why are you asking me to prove that greedy works now? All right. The difference is that the thing is that for coin change, you can solve it using like greedy methods. Only if the denominations that like the values that they give you like for example 1, 5, 25, 1, 2, 5. Let's say I give you like, okay, your coins can only be like $1, $5, $25, $125, that sort of thing, then it all works out. All right. For certain coin denominations, it does not work out. So the one that we gave you, so the one that we gave you at the beginning of for the DP assignment, like that doesn't work out, but the one that we gave you that we're giving you in this assignment should work out. All right. So these kind of problems, these kind of problems use like the greedy paradigm. Okay, I'll talk a little bit about MST if I have time for it, but if not, let me show you some examples of what I mean. Okay, so again, moving from this point, right, what you guys need to understand is that optimal substructure just says that, okay, if I'm solving my problems recursively, I should do my best solving my subproblems, right? It doesn't tell me which subproblem I should be looking at. It just says that if I did solve my subproblems optimally, I should be able to reconstruct my solution. Okay. Greedy choice, on the other hand, says that, hey, maybe I don't have to look at all my subproblems. Okay. And oftentimes this is really helpful. Like you might be able to speed up even more, like you might have like a solution that like, okay, like I look at it recursively and I said, okay, it's recursive, there's overlapping subproblems, let me just DP. Okay. That might give you an optimization, right? And then sometimes you you realize, oh, I should, like maybe I don't even have to recurse on all of them, just this one subproblem. And that saves even more time. Okay, so I'll show you some examples now. One other motivation is that sometimes when you try to use DP, there's really way too many subproblems to solve. And maybe there's not much overlap. But greedy will tell you what you're supposed to do. So you might have like this really, really big like possibility of like cases to consider, and DP just can't cover all of them, or DP can't save enough to like can't store enough of them to there's not enough overlap for it to save the time complexity of your algorithm. But greedy will just tell you, like the rest of these cases are rubbish. We really don't have to look at it. Okay, so I'm going to recycle. I'm going to hopefully like Ken allows me, Professor Ken, which is like the other professor, like the professor for the other module, like the other iteration of 3230 allows me to. I'm pretty sure he'll be fine with it. Let's just not tell him, even though it's gonna be on YouTube. I'm gonna recycle one question from last semester to motivate greedy, and we're gonna call it the CD problem. Okay, like this is gonna be like an artificial like real life problem. Okay, I'm gonna give you, let's say that you and I are like audiophiles. We really like music, and for some reason we want to store it on disk, or maybe vinyl. If you're like that kind of person. Okay, maybe vinyl makes more sense. But anyway, let's talk about CDs. So I have a bunch of file sizes. like let's say, what do I mean? What do I mean by file sizes? Like I have like audio files, right? Like music or songs or whatever, or maybe like recordings, right? And each of them have sizes. Okay. So let's say like I have like F1, F2, until Fn. So I have n of these files. Okay, and I have the following constraints. Okay, what I want to do is to put at most 2 files on disk. Okay, like on a single disk. So one disk, right? Even if it could hold more files, I'm gonna say screw it. I only want 2 files on this disk. Okay. So again, that like let's say my disk size is like my disk is of size, let's say like 100 or like some fixed value. I don't know. It doesn't really matter, but let's say it's a fixed value for now. Let's say 100. Okay. We can tweak the value later on. Like don't worry about that. So let's say I have a disk size of 100, right? So even if I have, like, say for example, 3 files and each file was of size 1, right? I'm only going to put 2 of these onto a single disk, okay? And I have like an unlimited number of disks. Okay, so we're kind of like at liberty to use however many disks we want, but of course we know we know from here that we only need n disks at most, right? And we're gonna assume that like for all I, fi is less than or equals to 100. Okay, so each of these can fit into a disk, so we know that we need at most n disks. Okay, but the point is that we want to minimize the number of disks we can that we're going to use. You know, like you might think this is ridiculous, right? It's like, hey, if you want to reduce, like, if you want to minimize the number of disks used, why don't you just put more files on the disk? Well, the answer is we can't do that, because if not, I don't have this problem. Like, I don't have this greedy problem to show you. Okay, so we're going to roughly again try to do the 3-step process, like for solving this problem. But we're gonna do a bit more than that. We're gonna sort of like realize that we can make a greedy choice here. Okay. Let me turn on my fan in my room before I continue, because it's getting kind of stuffy. All right. Everyone okay with the problem so far? Does it make sense? Right? Someone said something on chat. Sorry. Oh, okay. Close it by accident. Sorry. Okay. So we're clear with the problem, right? Like basically, again, you have n files. Each file is of size at not more than 100. Okay, and we want to put like at most 2 files on a single disk, right? And we want to minimize the number of disks involved. Okay, and of course we can't put like 2 files of size so that, okay, so I guess like I should mention this as well, but we can't have, what's going on? We can't have this. Oh, sorry, 3. We can't have that fi and fj. If fi and fj are greater than 100, you can't put them on the same disk. Of course, right? If not, this problem is easy. On same disk. Okay. Okay, so let's begin. Has anyone said anything? No one said anything. Okay. Sometimes I worry because when people don't say anything, I'm not sure if they're following. But I trust you guys. You guys would ask me, right? Yeah, nice. Okay. Yeah, but like maybe like the rest, you know, because like Terrence, you've been like active, but like the rest have like, well, you know, I don't know, maybe everyone's just shy. Okay, like I'll ask on Telegram if you don't want to ask now. Anyway, let's begin. So I have so let's try to solve this recursively, right? I have my solution F, okay, and I have like let's just say S is the set of the file sizes, right? I don't know. Let's pretend it's come in a sorted order if we want to. That should just take like n log n time, or I don't know. Okay, let's just pretend that it's come in sorted, so we don't even have to sort it ourselves. Okay, so we want a solution that given this set of file sizes, right, returns me some natural number which indicates the minimum number of files that I'm going to use. Okay. Now, as practice, I suggest what you do is that you when you go back and you revise this, if you want to, right? Again, this is optional. Prove that this problem is going to like have optimal substructure, right? In other words, you know, you're gonna like try to show for yourself, right, that this problem, like if you to solve it, to solve it properly, you're going to have to like solve the subproblems optimally, right? This applies to DP problems. This applies to like greedy problems as well. You have to show it, okay? So So what I'm going to do is I'm just going to show you like roughly what the solution should kind of look like. Okay. And then I'll show you the blank where we're supposed to fill in what's going to happen. Okay. So if I were doing this, recursively, right, without any regards to a what's it called, too greedy, right? To what I would do is I would just say try all possible pairings, Okay, and then like let's say like ij. What we want to do is we want to recurse on f of s, but we put file I and file j on the same. File I and file j on the same disk, right? Recursing on this means that, okay, I've taken these two out. And when I say possible pairings here, right, what I mean is, of course, like fi and fj should be like less than 100, right? So put all these pairings together, and then what we can do is we can plus one here, okay, and then recurse, right? And then say, okay, now these two files are out of the picture. Let's get it out of the way, and then we can solve for the rest, right? Then what you want to do is like your soft homework, quote unquote homework, is you want to show that like solving this optimally should like give you a better like solution than if you didn't, right? Or like I don't know, depending on however you're constructing your subproblems. The point is that you'll be able to get you should be solving optimally, okay? But anyway, the issue with trying all possible pairings here is that at every level you're going to be doing like n squared work, and every time you go down, you're going to be reducing the problem size by 2, right? That isn't great, right? Then you might think, okay, why don't we try to like dp this? And if you dp this, you might end up with like a dp table of size 2 to the power of n, because that's like you'll probably end up trying all possible subsets somehow, or most subsets, so maybe square root of 2 to the power of n. So DP wise, this might not be great, depending on how you do it. There like in my mind, I'm not sure how this works, but like I think there's a solution where if it's sorted, you can try to like move pointers in and try to infer how many CDs you can make out of that, or something like that. But I'm not very sure. Just random ramblings. Anyway, the point is that like even with DP, this doesn't seem very clear to me as to like how you're gonna make this fast. Okay, but we wanna strive for a good solution, because like this problem seems kind of easy. All right, so the way that we're gonna do this, is realize that over here, trying all possible pairings is kind of a useless exercise, and it's kind of like futile effort, in the sense that like you're really doing way too much work, and you actually don't have to recurse on all these subproblems, right? Like right now I have n squared subproblems, right? And that's just way too much time. Okay, I want to try for a good solution. So I wanna replace this with something better, and say that instead of trying all possible pairings, okay, I should be trying like for example maybe one pairing, and that pairing should be good enough. Okay. So the way that we're gonna do this, is that we're gonna swap out this part and say that we're gonna pick I and j such that fi is smallest and fj is largest, that still fit on the same disk. Okay, I mean intuitively the idea is going to be the intuition here kind of is that you're not going to waste space. Okay, but you can't just say take the smallest and the largest, because if they don't fit on the same disk, you can't put them on the same disk, right? So I think like the rough algorithm should be, if fj is too large, you should just put fj on a disk by itself. If not, you can put the two of them together on a single disk. Okay, so at this point, right, this is our greedy choice. This is going to like doing this selection, right? Doing this saying, hey, you two, I'm going to pick you. I don't have to care about the rest of the pairings, right? The reason why you wanna the reason why we can consider this, and you might be wondering, okay, why don't we consider other subproblems? Maybe we consulted the wrong one, right? We need to argue that this is the best subproblem that we're going to be solving. So like any other subproblem that we're going to be looking at, right, doesn't make sense. They're going to be giving solutions that either are like, you know, as good or worse, right, but never better. That's the point. Okay, so the proof idea here is going to be again, you want to do this whole swapping thing, right? This local swap argument. Oh, sorry, 1 second. This local swap argument. Okay, and the way to do that is going to be that you think about it and say assume not, right? Assume that that this was the bad choice, right? So this was the smallest. So my solution, right? This is our solution, right? Assume that this is bad. Okay, so I mark it in red because it's bad, right? Say that like there is some other optimal solution that doesn't do this. So in the other optimal solution, right? There should be two, like a disk, right, with two files together, right? And it's strictly less, by the way. So like this guy should have like strictly less CDs. Okay, so this guy has like some CD count. Let's call it O for optimal. This guy has some CD count. Let's call it C for count, right? So like this is the optimal count. Optimal solution has the optimal count, and our solution, our greedy solution, has like some count, which we're saying is strictly worse. Okay, so assume that in this case, right, like you shouldn't have made the choice to pair up Fi and Fj such that Fi is largest and Fj is largest, right? And is the smallest, something along those lines, right? Then it must be the case. It must be the case where that that they are like they belong on different disks, right? So let's say Fi is here, okay, and let's say that Fj is somewhere else, right? Fj is like this really big disk, and it's somewhere else. Okay. Now the thing is this, like you could also have like some other file here. It shouldn't matter. That's fine. Okay. The point is that they fit. Okay. So we want to show what I'm going to show is that this strict inequality, right, is a contradiction. Okay. Now the way to do that is the following. Okay. Think about it. What happens if I, instead of doing this solution, this optimal solution, right, tried my solution instead? Is it feasible? You know, just I don't care about the rest of the disks, right? They don't really they're not in the picture here, right? All I have to do is just look at these two disks and compare it to this disk. Okay, like this disk which has Fi and Fj. Okay, so what happens if I try to put this Fj and this Fi in the same disk instead, right? So I look at the optimal solution, I look at those two disks and say, okay, I'm looking at the two of you, can I swap you? What happens, right? So let me put these two in like, instead of having this solution, let me just put them in the same disk, right? We know that this can fit, right? Because by definition, by our assumption, they should have been able to fit together. We just didn't do it because it gave us an optimal solution, right? Now we need to argue that this guy can swap over here as well, right? This other guy that's accompanying Fi can move to the other disk and we won't have an issue, right? Well, we clearly wouldn't have an issue because if this guy was sitting on a disk with something else, right? We know that these two file sizes are less than or equal to 100, and we know that this guy wasn't the largest file size, right? Since he wasn't the largest file size, right? He couldn't have possibly moved. He couldn't have like overflowed the disk, right? Like basically the file sizes should not be greater than 100. So you can move this guy over, right? This guy's total file size should still be less than or equal to 100. This guy's file size should definitely be still less than or equal to 100, right? And we have the same solution, right? In other words, right, it's not with strict inequality, like it's not with a strict inequality, we would still have like a like equality, or like keep swapping it until this happens, right? Until you get all of these things worked out, right? So it can't be the case that we have a strictly better solution somehow by not following this greedy choice. By following this greedy choice, right, we definitely will not be missing out on an optimal solution. Does it make sense? Okay, so if we want to implement this optimally, like implement this efficiently, what we want to do is we want to have the file sizes sorted. Oh, sorry, happened again. We want to have the file sizes sorted. Okay, and then what we're going to do is that we're going to have two pointers. And we're going to ask the item at the left pointer plus the item at the right pointer, are you greater than or equal to 100? Right? Sorry, are you greater than 100? If you're greater than 100, throw this guy into a disk, forget about him. Move the pointer back. Right? If both files end up fitting on the same disk, put them both in a disk together and then move both pointers inwards, so on and so forth, right? If the input comes in sorted, you have this done in O(n) time, very fast. Does it make sense? O(n) is like probably the best you can hope for. Like if it's not sorted, just sort it first, then run this process. All right. Okay, before I take questions, again, send any questions you have to the Telegram chat. Let me quickly in 5 minutes, or 3 minutes, do one more. Okay, let me quickly do one more. So the next problem is a bit more abstract. It's kind of mathematical, so hopefully it's not too dry for you guys. The point is that I'm going to be given a sequence of numbers, x1 to xn. Okay, you can pretend that they're like real numbers. You can pretend they're integers, what have you. Like let's pretend they're positive for now. Like I think it makes life easier. Okay, and you're given y1 to yn. Okay, and the goal here for this last problem is that you want to show you want to find an arrangement of the yi's. So in other words, right, you're allowed to shuffle this guy. Okay, you want to shuffle it. So that so that what happens is that xi times yi, if you add all this up, this is minimized. This is equal to some value, let's call it s, and this is minimized. Okay, so the intuition here is that you can think of this as like you trying to zip up elements, right? So like if I were to rearrange this and then I did like I multiplied them pointwise and then added all these values up. Okay, of course shuffling it actually changes the possible values you can obtain. I want to find the smallest possible one. Okay, now if you wanted to solve this recursively, like again, I mean, you still need to show that this is optimal substructure, and I'll leave that for you to do in your own time. All right, but if you wanna show if you wanna do this via DP, you can think of it as possibly okay, like I am looking at the first item of x1, I should pick some item among the remaining values of y, multiply with this guy, and add on whatever is like minimal with the remaining elements, right? So like if I wanted to do this recursively, given like fx and fy, right, what I'm gonna do is I'm gonna pick some yi, and then I'm gonna say x1 times yi plus f of x without x1, right, and y without yi, right? Except again, doing this is very slow. You have like n subproblems, okay, and to index into each set, like I'm not sure how much space that will take, right? But it's gonna be like, I don't know. I'm pretty sure this is like at least n squared or something, right? Just by eyeballing it. Okay, so the point is that if we do greedy, this can be much faster, right? The way that we're gonna do it is that the intuition here is going to be that you should take small items of y, to multiply with big items of x, and vice versa. Okay. In other words, what you want to show is that if x was, let's say, arranged in increasing order, okay, so it's going up, what you should do is you should shuffle y, you should rearrange it so that y instead is going downwards. Then you should zip it up, then you should multiply it like this and add up the values. Okay. Again, you might be wondering, why should we do this? There could be a better solution. And you can think about how to do this recursively, right? So if you're doing it recursively, if it's already sorted, you should just like multiply two values together. Okay. So at this point, this means assume that's not the case, right? Assume that this is not the right way to do things. So let's just have this sequence lined up, right? So x1 to xi to xj to xn. And this is done in increasing order. And you have like y1 to yi to yj to yn. This is done in decreasing order. Okay. Now, you might be wondering, okay, what if we didn't follow this greedy strategy? Like is there could there have been a better solution, right? Well, okay, so let's assume that there was a better solution and you didn't follow this sorted idea, right? What that means is that there must have been some xi and xj, right, such that xi is less than or equals to xj. Okay, and there must have been some yj, which was supposed to be sorted downwards, but we said that we're not respecting that, right? So this must have also been the equality must have also been held like this way, yi less than yj, such that this gives you the best solution, right? So you multiply these two, you multiply these two, you multiply these two, and you add everything up. Okay, so this must happen, right? So then the question becomes, what if you swap it, right? What if we swap these two? What do we get? Right? So let's look at the original solution. The supposed optimal solution. The supposed optimal solution what it would have is xi times yi plus xj times yj, right? Plus like all this other stuff, right? All like this thing here, which I don't care about, this thing here, which I don't care about. The reason why I don't care about it is that when I swap it, right, these items are still going to be in the same position, right? So let's forget about that. All we care about is what changes are made like after the swap, right? Before and after the swap. So before the swap, this is the value that we get. Okay. Now after the swap, the value that we get should be xi times yj, right? Plus xj times yi. Okay. So wait, sorry, xj, yj, right? So I want to compare these two values. Let's just do a subtraction. Okay. Now if I did a subtraction, I can factor this out. It becomes, remember, this is our supposedly optimal solution. Supposedly optimal, right? This is the sorted solution. Okay. So if I factor this out, this becomes yi minus yj, okay, plus xj times yj minus yi. Okay, now I can rewrite this again. This is a minus sign here, but this is yj first and this is yi first. So I can just like swap this out and this becomes yi minus yj, right? Minus xj yi minus yj, right? Then since these two are the same term, right, I can factor this out again. This becomes xi minus xj times yi minus yj. Okay, now I know that xi minus xj is a negative value because this guy is smaller than this guy, right? And I know that yi minus yj is also a negative value because this guy is smaller than this guy, right? So negative times negative means it's a positive value, which means that this guy is greater than 0, right? And if this guy is greater than 0, what that means is that this original term, right, is greater than 0. What does that mean? That means that that means I can shift this to the right hand side. So our supposedly optimal solution is actually worse, right? Gives you a larger value than our sorted solution. Does that make sense? I know I was a bit fast on the math. Take a screenshot, I don't know, like you'll see in the video again. But this is the rough idea.
Albert, can I ask?
Uh-huh.
These indexes, right? Is this, I can't make it out. Is it I and J or?
Yeah, it's I and J. Oh wait, so this is I. This is
this one.
Oh, this one is I.
Oh,
that's J.
Okay. So you're doing nothing to the left side, right?
Yeah.
And then taking out the negative of the right side.
That's why I can factor it out, right? Yeah.
Yeah. Okay, understand.
Okay, cool. All right. Okay, sorry, today was a bit rushed. I'm just trying to like show you guys as much as possible, so at least walking into your assignment is not too painful. All right. But if you guys have any questions, send them on Telegram. Okay. I need to run off to the next class. Okay. With that, class is over. Hope you guys have a great week ahead. Let me stop sharing. Stop recording.